Hi, AP Psych. These are your Module 6 notes. So today we'll be focusing on correlations and experiments. I hope you're listening and doing these before you come to class on Thursday or Friday. This is something that we're going to be doing more practice with rather than activities. So be prepared to come with any questions that you might have. These concepts can be straightforward for some of you. For others of you, they might be a little bit more difficult. No matter where you are after you're done with this, hopefully by the end of class time on Thursday or Friday, you'll be perfectly clear on everything you need to know. So with that said, here we go. I wanted to start with just a little overview so you can kind of see what we've already talked about and then where we'll be going today. So with our research methods that we're looking at for psychology, they can be divided into three main categories. So we have descriptive research. This was our Module 5 notes, and we talked about case studies, naturalistic observation, and surveys. And then today's focus is going to be on these other two types, correlational research and experimental research. We'll be looking at the differences between them. There's a pretty big difference in terms of the types of results or what conclusions you can draw, depending on which type of the three that you're focusing on. So again, this is Module 6. So we're going to start with correlations. I have the learning targets for you for correlations, and then we'll go to experiments. So the essential question again is, how does the methodology of research affect the outcome of a study? Our learning targets are, I can differentiate between different types of research with regard to purpose, strengths, and weaknesses. 2, I can describe how research design drives the reasonable conclusions that can be drawn. And really that's looking at the type of research that I do helps to define what type of information I can get. 3, I can distinguish between random assignment of participants to conditions and experiments and random selection of participants, primarily in correlational studies and surveys. And finally, I can apply basic descriptive statistical concepts, including interpreting and constructing graphs and calculating simple descriptive statistics. So today we'll look more at the interpreting and constructing graphs. The calculating descriptive statistics will come with Module 7 that we'll get to next week. So first, to tell you a little story that I think helps to illustrate this idea of correlations, and this is the story of Joseph Goldberger and pellagra. Okay, so what they were looking at is in the early 20th century, there were thousands of Americans in the South who were dying from this disease called pellagra. And it's a disease that causes things like dizziness, lethargy, running, sores, and vomiting. And they were finding that families struck with the disease often had poor plumbing and sewage, which led many physicians to conclude that pellagra was transmitted by poor sanitary conditions. However, Dr. Goldberger here, who was the Surgeon General, thought that the illness was caused by an inadequate diet. He felt that the correlation, we're going to learn that just means relationship, so correlation or relationship, between sewage conditions and pellagra did not reflect a causal relationship, but that the correlation arose because the economically disadvantaged were likely to have poor diets as well as poor plumbing. So in order to resolve the controversy and be able to say definitively, he designed an experiment using the experimental method. So this study is going to help us clarify the difference between what we can find out from correlational research versus experimental research. So here's what he did. And this is talk about being involved in your research. So to prove he was right, Goldberger had himself injected with the blood of a pellagra patient. He also went a step further. So he selected 2 patients, one with scaling sores, you can see on the people in these images here, and the other with diarrhea. He scraped the scales from the sores, mixed the scales with 4 cubic centimeters of urine from the same patients, added an equal amount of liquid feces, and rolled the mixture into little dough balls by the addition of 4 pinches of flour. The pills were taken voluntarily by himself, by his assistants, and, if you want a definition of love, by his wife. Okay, so they all literally ate the excrement and the scaling sores of pellagra patients. Okay, so think about if it was due to poor sanitary conditions, if that was in fact the cause, one of these people would probably come down with it, right? Here's the thing, none of them did. So none of these people that ate these poop pills, for lack of better words, none of them got sick, okay? But that still didn't prove that he was right in terms of poor diet, okay? So now, to further his case, this is where an experiment is going to come in. He asked 2 groups from a Mississippi State prison farm to volunteer for an experiment. Okay, so now we're going to divide this group of people, this population, into 2 groups. Okay, one group was given the high carb, low protein diet that Goldberger suspected was the actual cause of pellagra, while the other group received a balanced diet, so a mixture of carbs and protein. And within months, the group who was given the high carb, low protein diet was ravaged by pellagra, while the group given a well-balanced diet showed no signs of the disease. So by doing that second step, he did what we'll know as an experimental method. And when we run an experiment, we can tell cause and effect. Okay. What he did before, just eating the poop pills, we weren't able to draw that full conclusion until we do the actual experiment. And what this story really should tell us is just because 2 things appear to have a relationship doesn't mean they actually do. Okay. So what I want you to take from this is this phrase. I want you to write it big in your notebook, highlight it, color it, star it, underline it, whatever it is you need to do. And that's correlation does not mean causation. Okay. So correlation, what this breaks down to, correlation, meaning a relationship between 2 variables, does not mean that one caused the other. Again, just because 2 things appear to be related does not mean that one caused the other. So just because in the pellagra story, just because it seemed to be a relationship between poor sanitary conditions and people having pellagra does not mean that poor sanitary conditions caused pellagra to develop. Okay, in fact, it could be something else. In that case, poor diet. So now let's talk about what is a correlation. We have some idea now, but a correlation is defined as the measure of the extent to which 2 variables change together, affect each other, essentially, and thus of how well either variable predicts the other. Okay. Again, what I think of in my mind is what is the relationship between these 2 things? If we compare that to causation, okay, causation is where changes in one variable directly cause changes in the other. Okay, so again, correlation, how do they change together? How do they affect each other? With causation, it's one directly causes changes in the other. Okay, and one thing I'm going to say over and over again, the only type of research methodology that allows you to determine causation is an experiment. If there's any sort of survey, a case study, a naturalistic observation, anything like that, they cannot tell cause and effect. So when we talk about relationships, that feels very abstract. What do we mean by how does one variable affect another? How does one variable change with another? Okay. The way that we measure this, put it into something quantitative, okay, similar to what we talked about with with operational definitions, there we go, is through an actual number. It's expressed as the letter R. For those of you that are taking stats, this is something you talk about in your stats class. Okay, this is a correlational coefficient. So this is a statistical index of the relationship between two variables, and this number is always somewhere between -1 and +1. Okay, -1 to +1. And the closer to either -1 or +1 indicates a strong relationship. If it's closer to 0, it indicates a weak relationship. Okay, and I'll clarify more for you. So here's what that might look like. So negative correlation, we can have a negative correlation or a positive correlation. And what that tells us is what is the direction of the relationship. So a negative correlation implies an indirect or inverse relationship. So as one variable goes up, the other goes down. Or as one goes down, the other goes up. So for example, a negative correlation is as you watch more TV, so number of hours TV watching goes up, your GPA goes down. So that's a negative correlation. A positive correlation is a direct relationship, meaning both variables go in the same direction. So as you study more, your grades go up. Okay. As you study less, your grades go down. Those are both positive correlations, even though we're talking about something going down, because both variables move in the same direction. That's key. Okay, it can be going down as long as both variables go down. Okay, the less you eat, the less you weigh. That's a positive correlation, even though both are going down. Okay, the more you eat, the more you weigh. Also a positive correlation. So let me go back to this real fast. Okay, I want you to think, this is where I really wish. Discover new things. Okay, let me see if I can draw it out for you. I want you to think of a number line here. This is a 0. We're going to see how good I am drawing with the mouse. This is +1 over here. This is -1 over here. Okay. The closer you get to 0 indicates a weak relationship. Okay. The closer you get over here to positive equals strong. This is a challenge, I'm telling you, with the mouse. Okay. And over here, -1 is equally as strong. So notice that -1 and +1, equal amount of strength. So the closer it moves this way, stronger. Closer it moves this way, stronger. Closer it moves to the middle, to 0, weaker. Okay, now let me go to this next slide here. Oh, that's going to stay. Well, let's leave this up. Maybe this will help you on here, and then I'll erase my drawings. Didn't know that it did that till right now. Okay, so which of the following correlation coefficients presents the strongest relationship between the variables? So go ahead and look at your options. You can use my attempt at a number line here to help you out. Go ahead and select your choice. Okay, so the correct answer here is -0.77. Okay, here's why again. This number, -0.77, is the closest to either -1 or +1. Okay, it doesn't matter that it's negative because it's as close to +1. It's closer than, say, 0.55 is only maybe here. Okay, 0.77 is more closer to either the -1 or the +1. If we change the question and said which one presents the weakest relationship, okay, the correct answer would be A, because it's closest to 0. Okay, so now I'm going to erase this. Again, I'm learning new tricks on the fly. Did not know I could do this as I'm recording. So let me erase. That way you can try it without the number line on the next one. Okay, back to my pointer. Here you go. Next one. Which of the following correlation coefficients presents the strongest relationship between the variables? Go ahead and choose again. Okay, the correct answer for this one is 0.79. Again, because it's the closest to either -1 or +1. If we were to flip this and it asks for the weakest relationship, the weakest here would be C, 0.00, because that's closest to 0. Okay, here we go. Now, which one presents the weakest relationship between the variables? Okay, the correct answer is 0.02. If we would have flipped it and it was the strongest relationship, it would be -0.77. One more. This one I already kind of told you. Which one presents the weakest relationship? The correct answer is 0.00 because it's closest to 0. If you have questions, make note of it so that I can explain to you. I'm going to ask if there's any questions so I can explain to you on Thursday or Friday when I see you. Okay, so we know it can be this idea of a relationship, a correlation can be expressed with R or with a correlational coefficient, but this is also a relationship we can express via graph called a scatter plot. So a scatter plot is a graphed cluster of dots, each of which represents the values of two variables. So the slope of the point suggests the direction of the relationship between the variables. So if it slopes up to the right, this indicates a positive relationship, meaning the variables are moving in the same direction. Okay. Increased sleep, increased grades would be both moving up, positive correlation. Okay. A negative correlation points down to the right. So this is where the variables are moving in opposite directions. The more TV you watch, the lower your grades go. So we would see it sloping down to the right. Okay. If you have no correlation, notice that the dots are scattered all over the place where you can't make out a line. Okay. What you see here, look at this very left, the perfect positive correlation. That would be the correlation coefficient of positive 1.00. And then a perfect negative correlation, negative 1.00. Notice it's a perfectly straight line. Okay. The amount of spread from that line is called the line of best fit. The amount of spread from the line indicates the strength of the relationship. So the closer you get to a perfectly straight line indicates a higher correlation. The more spread out, notice here you can't make out any sort of actual line, either positive or negative, indicates a weaker or no relationship. So let's practice this idea. So if you take a look here, we have these various different correlations. Okay. I want you to think about, and we can do this. Let's do this. Let's number these 1, 2, 3, 4, and 5. I want you to go through and type in your answer. If you had to take a guess of a correlation coefficient for each of these, I want you to put number 1, what you think it is, 2, what you think it is, and so forth. Go ahead and type those numbers in the question box now. Okay, so for number 1, and this isn't exact, I actually don't know the exact correlation coefficients for these graphs, but I can give you an estimate. If yours is pretty close, we'll accept it as correct. If you're way far off, then this is something you need to bring up on Thursday or Friday when I see you so we can go over it again. I also have some retrieval practice with some different graphs for you to practice on too. Okay, so for number 1, I would say it's somewhere because it's positive. Okay, it slopes up to the right. I would say positive 0.7, 0.8. Because notice you can very easily make out where that line of best fit would be. We don't have too much scatter, so it's a fairly high positive correlation. So plus 0.7 to 0.8 here. Okay, I would want them a little bit closer to the line to get up to a 0.9. Okay. Similarly here, okay, I can make out that line of best fit fairly easily. This would be negative 0.7 or negative 0.8. That's a high negative correlation. Okay. For number 3, I want you to notice you can still kind of make out where a line would be, but it's more spread out. This one is probably closer to a 0.5, 0.6. Okay, probably 0.5 or so. You can still make out a line, but we definitely have more spread. It's a positive. It slopes up to the right. That tells me both variables moving in the same direction. Here, very similar to number 3. You can kind of make out the line still, but more spread out than what we saw up here. So this would be around a negative 0.5. Okay. And now this one, notice there's no way you can make out any sort of line of best fit. This means just by saying no correlation, you should know it's a 0.00. No correlation here. All right, let me erase these so my numbers don't stay on my next slide. All right, here we go. So some other things to make note of with correlation and causation, okay? Correlation coefficients, okay, again, that number between -1 and +1, do not indicate the direction of the relationship, just that a relationship exists. So that's really important to make note of. So for example, if we're talking about low self-esteem and depression, one direction the variables could go is low self-esteem could cause or lead to depression, or perhaps depression could lead to low self-esteem. So notice we don't know. We can say there's a correlation between low self-esteem and depression. We could find out a correlation coefficient. We could graph it on a scatter plot, but we don't know what is leading to what. Okay. It could be something else. It could be some sort of distressing event, some sort of biological predisposition could lead to both low self-esteem and depression. Okay. So you need to be really mindful that, again, just because something is correlated does not mean that one causes the other. It could, but we would have to do an experiment to know that for sure. The other thing to be aware of, this will be our last slide about correlations before we move on to experiments, is something called an illusory correlation. This is the perception of a relationship where none exists. Okay, for example, the lunar lunacy effect is this idea that during a full moon, people act really strangely. But in fact, that's an illusory correlation. So we think there's an association there when in fact there is not. And often these are influenced by confirmation bias. If I already think it's true, if I already think people act strange when there's a full moon, I'm going to search for events to help prove it's true. But there could be events happening when there's not a full moon and I'm just not looking for them. So be mindful of illusory correlations. All right, that brings us to experiments. So again, same essential question. Very similar learning targets. We're going to add a little bit more, okay? So one, I can differentiate between different types of research, again, with regard to purpose, strengths, and weaknesses. 2, I can describe how research design drives the reasonable conclusions that can be drawn. 3, I can identify independent, dependent, confounding, and control variables in experimental design. We will spend a lot of time in class practicing looking for those ideas. And finally, I can distinguish between random assignment and random selection. So to get us started, here we go. So first, let's define what do we mean by an experiment. So an experiment is a research method in which an investigator, researcher, manipulates, i.e. read that as changes something about one or more factors to observe the effect on some behavior or mental process. Okay. So with an experiment, as a researcher, I'm literally changing something about someone's situation. Okay. And then measuring what does that do. So for example, if I was doing some sort of study on a new medication, I want to know if the medication works, I'm going to use an experiment. And what that means is I'm actually going to give someone the medication. One group of people, I'm going to give them the actual medication. Another group of people, I don't give them medication. Okay. Giving them the medication is what I'm manipulating. I'm changing about what their situation. That's my independent variable. And then I'm going to observe what happens. Does the medication actually work? And the measurement is the dependent variable. Okay. When I do this type of research, this is the only type, okay, that can determine cause and effect. You need to highlight, underline, star, really important to remember and understand. Okay, so notice I'm going to use that same medication experiment as an example as I walk you through some of these other ideas. So one thing notice I said in my description is I'm going to take a large group of people. This is my sample. Okay, think of similar to what we learned about with surveys. So I have a group of people that are participating in my study. Okay, I'm actually going to divide those people up into multiple groups. So let's talk about what that looks like. Okay, I'm going to divide them up into at least two groups. One group is going to be called an experimental group. My other group is going to be called a control group. Think of that as the comparison group. Okay, if I'm doing an experiment about a medication, my experimental group is going to take the actual medication. So they're the group that's exposed to the treatment or the independent variable. Okay. Say it's an antidepressant. The experimental group gets the actual antidepressant that I'm trying to see if it works. We've been hearing a lot lately about trials for a COVID vaccine. The experimental group gets the actual vaccine that they're testing. Okay, in that case, the vaccine itself is the independent variable. Okay, the control group is my comparison group. They get a placebo. So if a medication, my antidepressant, they get a fake pill that looks like the real thing. In a vaccine trial, they get injected with an inert substance that's safe. It's like, think of it like water. Okay, there's nothing actually in it. And what that does is it gives me two groups to compare against each other. So again, experimental group, exposed to the independent variable, control group does not. So how do we decide who goes into what group? We have to pay attention to that in order to reduce bias. So the way groups are selected is through random assignment. Okay, make note, this is going to be different than random sampling. Random sampling is done with descriptive research. Random assignment is done with experiments. Okay, so random assignment is assigning participants to experimental and control groups. You may want to highlight where you see my mouse moving, by chance. Okay, thus minimizing any sort of pre-existing differences between the groups. Okay. And again, sometimes you do have a random sample, like all these people that want to participate in a COVID vaccine trial. They're selected out of a larger population, a lot of times selected at random. So we get a wide range of types of people. But for experimental purposes, we're focusing on now, I have this population, this sample, this group of people, and I'm going to divide them into two. Okay, divide them into two. What this is called is between subjects design. So in the COVID vaccine trials, you have a group of participants. They flip a coin. If it's heads, they go into the experimental group. If it's tails, they go into the control group. Okay. The experimental group gets the actual vaccine. The control group gets a placebo, a fake. Okay. That's between subjects design. There is another type called within subjects design, where participants are compared to themselves. They take like a pre-test Then they're exposed to the independent variable, and then they take a post test. That would be similar to what we talked about with our scientific method, where people were given a memory test before, then they slept or didn't sleep, and then take another test after. That's a within subjects design. So a little bit more, how are they, again, selected? So let's say I have a group of babies, toddlers here, okay? And I want to know the effect of breastfeeding on intelligence. So that's what I'm studying. Say my hypothesis is infants that are breastfed have higher IQ scores than those that were not. Okay. I take my group of babies, and for each baby, I flip a coin. Okay. If it's heads, they're in the experimental group. If it's tails, they're in the control group. Okay. So now I've divided them using random assignment. Notice I don't pick out the babies that I want to add to each group. That could lead to bias. So it has to be random. They're randomly assigned to one of two groups. Okay. My experimental group is, again, exposed to the independent variable. I promote breastfeeding for them. My control group, I do not promote breastfeeding, or I might say they need to be bottle fed. And then I measure my dependent variable. Okay, I measure via an intelligence score. If I were to bring up, let me back up, to remind you of something we talked about before on Tuesday and Wednesday of operational definitions, I would define this further, an intelligence score on the Wechsler intelligence test. That's an actual name of an intelligence test. So I would say that specifically as my operational definition of the dependent variable. That's a lot, right? Let's pause for a minute and let's see where we're at. So I'd like you to answer this question for me. I want you to explain the difference between random sampling. You got to refer back to Module 5. That's what we talked about with surveys. And random assignment that's used with experiments. So take a moment to answer that. Okay, some key things you want to look for in your definition. Again, with random sampling, it's literally randomly selecting people out of the population to participate in your survey, where everyone in the population has an equal chance of being chosen. Random assignment is specific to experiments, where I'm randomly coin flip, draw a number, whatever the selection process is, and I'm assigning them to either the experimental group or the control group. So random assignment is only done with experiments. One of the reasons why random assignment is so important is it's one way to help prevent bias. Okay, there are some other ways as well. So one way is through what's called a single blind procedure. This is a procedure in which the research participant, say the person being injected with the vaccine, does not know whether they've received the actual vaccine or a placebo. So they're injected with something, they don't know which thing it was. If they're taking a medication, they don't know which one it is. Okay, is it fake pill, real pill? In a double-blind procedure, not only is the research participant blind, meaning they don't know, but the person, the research staff who is administering the vaccine or the medication is also blind. Okay, think about why that might be important. If I'm the one administering the vaccine and I knew I was giving you either the real or fake one, I'm a human being. I might have a hard time keeping a straight face. If they ask me, am I getting the real one or the fake one? I might accidentally give it away if I know. Okay, so this is a means to prevent bias. If I don't know what I'm giving you, I can't give anything away. So I want you to take a moment and explain the difference between a single blind and a double blind procedure. So again, key thing, single blind, only the participant is blind. In a double blind, both the participant and the researcher both don't know if someone is part of the experimental group or the control group. One last idea before we talk about the variables a little bit. This is the placebo effect. Okay. Sometimes just thinking you're getting the real thing can cause you to have symptoms or to experience effects. So these are experimental results that are caused by expectations alone. So if I'm in an antidepressant drug trial, drug experiment, let's say I'm given the placebo, I might report feeling happier just because I think I might be getting the medication, even if I'm not. Okay. This top one with the bear, my meme. My sister had a headache and we ran out of Advil, so I gave her a Skittle with a glass of water. The sister might report feeling better just because they think they took something that could help them. A placebo effect is just something that we need to be aware of and why we need to randomly assign so that people don't know, and why we need to use preferably double-blind procedures so that people don't know. So if we're comparing groups, the experimental group versus the control group, hopefully any differences that we see are because of the independent variable and not because of something else. So let's talk about these variables a little bit. We're almost done, but I want to describe this a little bit more for you. One of the things that you will need to be able to do is read a research study and be able to identify which variable is the independent variable, which variable is the dependent variable. Okay, so these are some mnemonics that I've used. So the independent variable is the experimental factor that is being manipulated. I use the I in manipulate to remind me of independent. So this is the variable whose effect is being studied. A lot of times you can identify it by asking, like, what is the point of this study? What are they trying to do as in doing the study? So in a vaccine trial, in a COVID-19 vaccine trial, they want to know, like, does this vaccine actually work? Okay. So the independent variable is the vaccine itself. In a drug trial, the independent variable is the medication itself. Okay. The dependent variable is the outcome, what's being measured. That's why I have the measuring tapes there. It's literally, what am I measuring? What did I observe? Okay, so in our vaccine trial, the independent variable is the vaccine itself. The dependent variable, what I'm measuring, is, do people get COVID? In my depression drug trial, the independent variable is the drug itself. The dependent variable is their level of depression. Does it change? The other type of variable I need to be aware of are confounding variables. These are other factors that may affect my results outside of the independent variable. So confounding variables, there can be tons of other things. Sometimes they're called third variables or expounding variables. So it's something else that could affect my results. So for example, in my vaccine trial, I know my independent variable is the vaccine, but what else might affect my results of, do I get COVID or not? It could be a confounding variable is, am I exposed to someone with COVID or not? Am I in close proximity? Do I have some sort of underlying condition that makes me more susceptible? Okay, all of those are confounding variables. And one of the things that we can do to control for confounding variables is random assignment. Knowing that we can never have perfect clones of each other to participate in our studies, but with random assignment, we can at least help to limit the effects a variable has on my study. The last actual slide, and then I'm going to give you a little bit of practice, okay, is this idea of validity. We'll be talking about this again when we get to our intelligence unit, so this is a little introduction. But validity means the extent to which a test or experiment measures or predicts what it is supposed to. So if an experiment or research is valid, it means it actually tests or measures what it is supposed to test. So if I'm doing a vaccine trial for COVID, okay, Does my vaccine trial actually measure whether someone gets COVID or not? If it does, it's a valid experiment. It doesn't mean valid doesn't mean my results are good. Valid doesn't mean my hypothesis is confirmed, but simply doesn't measure or predict what it's supposed to. So now I have a little sample exercise for you. So we're going to use this same study, and I'm going to have you identify the various variables. So a high school track coach is interested in the impact of carbohydrate consumption on running times in her athletes. She asked half of her team to eat a huge pasta dinner the night before a big meet, and asked the other half of her team to eat a large steak and no carbohydrates. Identify the variables in this experiment. So the first one I want you to identify is the dependent variable. So go ahead and type your answer. Okay, so remember, dependent variable is what is being measured. So in this case, she's measuring running times. So your dependent variable should have been something related to running times. Okay, next. Same scenario. Now I want you to tell me what is the independent variable. Go ahead and type your response. Okay, in this case, one way you can help determine is notice that she put them into two groups. Half ate big pasta dinner, the other half ate large steak and no carbs. If you look at what's different about the groups, that difference is the independent variable. So in this case, it's what did they eat? The amount of carbohydrates they ate. Okay, finally, give an example of a confounding variable. Go ahead and type. So confounding variables, we could have lots more variation. It could have been what else affected running time, anything else that could have affected running times. It could have been if athletes were sick. Were some more well-conditioned than others previous to this test? Did they sleep the night before? Did they have a bad breakup? Okay, lots of different things could be confounding variables. As long as you said something that could have affected the athlete's running times that is not related to food. Okay, and pretty much anything else could go. So hopefully you followed along with all of this. In class, I have lots of practice that we'll be doing. Come to class with your questions, and I will see you all then. Have a great rest of your day.